Hello everyone. In this video, we are going to talk about wave equation. So we are going to continue there. And I'm going to deduce a formula which is called D'Alembert's formula. A very useful formula. And let's just see what exactly does it say. So essentially, we are looking for a wave equation, right? So this sort of equation, utt minus c square uxx is equals to 0. Clear? And here, I am assuming x to be in R, right? And t is positive. So in the earlier case, if you remember, we assumed x is like between 0 and L. So there is this finite string kind of thing. This is like the infinite version of that, right? So here x is in R and t is greater than 0. Clear? So upper half plane, you can think of it like this. And there are some initial conditions here. Initial condition, what I mean is at the point, so when time equals to 0, right? So you remember in the earlier just the video, we talked about two sort of condition. One is the initial condition and there will be something called a boundary condition, right? So here in this sort of problem, we are just, we'll be interested only on the initial conditions, okay? So let's just see and then I will explain to you what all of this means. Okay, so the initial condition is essentially what I mean is as t equals to 0, some information is given, f of x. So u restricted to the point t equals to 0 is f of x, and again ut, right, the initial display, so basically velocity with respect to time, so that at t equals to 0, that will be given by g of x. So this is some function f and g, nice enough function, we'll just assume that, yes. So x is in R and here also x is in R. Is it okay? Okay. Now the point is this, we want to solve this problem with this initial data. So how do I solve it? Now, of course, you know those things, right? That we can talk about the characteristic equation. So of this problem, we have already talked about it. Yes. So we can do all that. So by using the characteristic method, so using, let me write it like this, using the method of characteristics. So essentially canonical form, or maybe let me do it like this. So let me refer to the canonical form video. So as you can look at this form and you can see that this is the second canonical form for a hyperbolic equation, right? The other canonical form looks like this: uxt, that's the higher order term, plus some lower order term, right? That is the first one. So we want to put it in that form. Let's just see. So refer to canonical form. Yes. And what we do is, in canonical form, you remember we talked about two different variables. So we change the variable. Yes. And the thing is this, so the characteristic curves which you are going to get. So I'm not doing all that. Yeah, you can of course do it. So therefore, the characteristic curves of the equation, characteristic curves are given as x plus minus ct equals to some constant. So basically there will be two constant, x plus ct, there is one constant c1, and then x minus ct, there will be another constant c2. So but I am just writing it like this. Yeah. Okay. So you remember how we introduced those two change of variable? Yes. So what we were doing, we were actually using the characteristic curves to define two new variables xi and eta. Yeah, such that, so using this characteristic curve, so basically in this case we will define xi as x plus c times t, and what is eta of xy, sorry, this is xt, this is xt, and this is eta of xt, we will define it to be x minus ct. Yeah, you remember the variable we will choose the variable in such a way that if you restrict the variables on the characteristic curve, they are going to be constant. So as you can see, this is true. Yes. Okay, so if this is the idea, then xi and eta will choose it like this, and you can actually have the chain. So using chain rule, this you have to check, using chain rule. We have already talked about this thing, so I am not going into details here. So what do we get? You get that this equation, you can write it like this: uxx equals to u xi plus 2 u xi eta plus u eta eta. Clear? And then utt, that can be written as c square times u xi minus 2 u xi eta plus u eta eta. Is it okay? Yes. So once you get this, you see we have to put it in our equation. Which equation? This equation. Let's just call this 1, 2 and 3. So we'll put this in the equation 1. Okay. So putting it in equation 1, we have so this equation actually get transformed to a canonical form. This is also canonical form, but we will transform into a much easier form. So that will look like this: minus 4c square u xi eta, this is equals to 0. And since c is not 0, that we are assuming here, yes, c is not 0. So since c is not 0, that will give you u of xi eta is equals to 0, since c is not 0. Clear? Okay. So what do you have? U of xi eta equals to 0. This is the canonical form. This is the first canonical form. Of course, this is also in canonical form. See, 1 is the second canonical form. Second canonical form of a hyperbolic equation. Canonical form of a hyperbolic equation. Okay. But the thing is, it is a very nice form, of course. But the thing is, this is not enough to solve the problem. Yes. But the first canonical form, this is the first canonical form, if you remember. This is very easier form, right, to solve it. So you do realize if u xi eta is equals to 0, we talked about this form, right? Then what is u of xi eta? Okay, how do you get it? It is essentially integral xi star eta d eta plus some function phi of xi. This is okay. Yeah. So here this where phi star, maybe I can just write, oh, there is no point writing phi star. Let me just do it like phi. Okay. Where phi and psi and phi are arbitrarily smooth function. Smooth function is at least continuously differentiable. Here, smooth functions. Okay, so of course we can, you see, the thing is this particular thing, or maybe you can just write it like u star. Let's just write it u star. Okay, see, this thing we can just write it like this. Therefore we can write this xi eta, this is some function of eta, right? So you can write it as, we'll write it as xi of function eta plus phi of xi. One second, I made some mistake. This is eta, this is eta. This is it. Clear? Yeah. Where what is phi? Phi is nothing but integral phi star. Yeah. This is what we are just defining it like this. So don't worry about it. Yeah. This is some arbitrary function, so we can just define it like this. The idea here is you can be written as a function of eta plus some function of xi. That's the point. Yeah. And now if you change it to x on t variable, hence u of x comma t should look like some arbitrary function phi of x minus ct, okay, plus phi, another arbitrary function phi x plus ct. Yeah, I think I took xi to be x plus ct, right? Xi to be, yeah. So this is fine. So where phi and psi and phi are smooth arbitrary functions, arbitrary functions. Clear? Okay, now you see we have to have some initial condition satisfied, right? What is the initial condition? F of x equals to u of x0. Clear? So what is it? It is phi of x plus psi of x. Clear? And g of x is nothing but ut of x0, right? So if we calculate it, it becomes c times phi prime of x minus c times psi prime of x. Is this okay? Yeah. So let's just call this thing as 4 and let's just call this thing as 5. Clear? Now you see, if we integrate 5, yeah, so integrating 5 we have phi of x minus psi of x. This particular form, this looks like 1 by c times x naught to x, okay. X naught is some arbitrary constant essentially, z of tau d tau plus some constant k, okay, where x naught and k are arbitrary constants, right? You will get it. Yeah, this is just an integration. Again, you see, this is given phi x plus I x equals to f of x. So we can put everything together, right? So you see, therefore, if you put all this thing together, what is phi of x in this case? Therefore, what is phi of x? Phi of x is nothing but half times f of x plus 1 by 2c and then x naught to x g of tau d tau plus k by 2. Is it okay? And another one is psi of x, right? Psi of x. So what is it? It is half times f of x minus 1 by 2c, okay, x naught to x g of tau d tau minus k by 2, minus k by 2. Here, see, this is one equation and this equation 4. So if you subtract those two, you are of course going to get this particular form, right? Hence, the general form. So what is the solution? U of xt. Our solution is this. It is, you remember, you see, u of xt is this, right? Phi of x minus ct plus phi of x plus ct. So if we put all of this together, you see phi and psi, phi and psi, this we already know. So if you put it together, it becomes half f of x plus ct plus f of x minus ct. Yeah, I think you have seen this thing. Yeah, you remember last part we had similar sort of thing, right? Plus in separation of variable, yeah, 2c, it is x naught to x plus ct and then g of tau d tau minus x naught to x naught minus ct g of tau. Is this okay? So this is what you are going to get. So that is equals to half times f of x plus ct plus f of x minus ct. Here, plus putting this thing together, if you put it together, it becomes x minus ct to x plus ct g of tau. Here, so this is this equation. So this formula, this is a very important formula. It is called the D'Alembert formula solution for the Cauchy problem. Okay, so this formula, the above formula is called the D'Alembert's formula, for the one-dimensional Cauchy problem, 1D Cauchy problem. Is it okay? Right. So now that we have this, yes, let us understand some basic ideas of the problem, the solution. Yes, okay. See, anyways, see, let's say if we so that's your solution, of course. Now, how do you know this is a solution? Of course, you can just take this u of xt. You can take twice derivative with respect to x. You can take twice derivative with respect to t, and you can see that they are going to be essentially same. And of course, this satisfies the initial condition. That is trivial to see, right? So this is true. Of course, here the assumption is f and g are so here it is assumed that f has to be at least c2 and g is c1. This is our assumption, right? Okay. So with this assumption, this is always true. Okay. Now you see there is a small note which I want to put here. So let's write it as note. So what is it? It says that the value, you see, u of xt, let's say xt is a point, right? So u of xt it depends on the initial values of f, right? So it depends on the initial values of f, right, at the point x minus ct and x plus ct. See, c is given to us. This small c, this is given to us, right? Now, I want to find out what happens to u at the point xt. So the first part is f of x plus ct plus f of x minus ct. If x and t is given to us, we know what is x plus ct is, and you know what is x minus ct is. And f is given to us, so we know what f of these two particular thing is. So the first part actually depends only on the value of f at the endpoints x plus ct and x minus ct. Yes, so it does not depend on anywhere. We don't care about what happens to f inside. So we just care about what happens at x plus ct and x minus ct. C will be given to you. Okay. And also we need to know what g does, but not on the end point, but everywhere inside the those 2 points. So you see x minus ct, let's say, and x plus ct, these 2 points. See, we only need to know what f does at these 2 points, and we need to know what g does at within this whole domain, right? Okay. So the thing is this, you see, so you do realize that domain is very important, right? Okay. So you see, outside this domain, what f and g does it really matter to us? Does it really contribute to the solutions? What I meant is this: let's say if you want to find out what u does at the point xt, you just need to know what f does at those 2 endpoints and what g does in the middle of these 2, right? So if you take any point outside this interval, that doesn't have any effect on you. Is it okay? So this interval is very special. It's called the domain of dependence. So essentially, there is something called a domain of dependence. Okay. Dependence of the variables xt. And this domain of independence is basically this domain x minus ct and x plus ct. Is this okay? Right? So you understand why it is domain of dependence, because the solution only depends on what f and g does only on those 2 points or inside those interval. Nothing, it doesn't matter what it does outside. Is it okay? Right. Okay. Now the thing is this, we also need to know whether this solution, it depends continuously on the initial data or not. Okay. So you see, we'll also put this as a remark. So this is the third part of well postness, right? The solution so obtained, okay, depends continuously on the initial data. What does it mean? It means that the initial data, if you change the initial data a little bit, the solution also changes a little bit. Of course, it doesn't really make much mathematical sense as to say something changes a little bit. So let me just give you an exact form of what I'm trying to tell you. So for every epsilon greater than 0, right? For every epsilon greater than 0, so you start with a very, very small number. And for each time interval, 0 less than t less than t naught. Is it okay? So there exists a delta which depends on epsilon and t naught, such that, okay, so essentially we will have a delta which will depend, of course, on the epsilon and this time interval wherever we are bounding t naught, such that u of x of t minus u star of x of, I will explain to you what all of this means. This is less than epsilon whenever the initial data are small enough. So what is it? Initial data is f and g, right? So initial data f of x minus f of f star of x, sorry. This is less than epsilon, delta, and mod g of x minus g star of x this should be less than delta. So if both are less than delta, then u should be less than epsilon. Yes. Okay. So let's look at the proof of it. So what is the solution? You see, and what is u? And u star, u is the solution corresponding to f and g, right? So if you are given f and g, the solution which you are going to get is u, and if you are given f star and g star, the solution which you are getting via D'Alembert's formula is u star. This is what the idea is. Clear? Okay. So you see, u of xt minus u star of xt, the modulus of that is can be dominated by half times integral f of x plus ct minus f star of x plus ct, right, plus half of, so I will just put modulus everywhere, right? So I have this inequality, it is x minus ct minus f star of x minus ct. Clear? And then there is another term 1 by 2c, and this is x minus ct to x plus ct, and then you have g of tau minus g star of tau d tau. Is it okay? So you write all of this together and then you use triangle inequality. So this is via triangle inequality. Yeah. So write D'Alembert formula for this, and then use just triangle inequality. This is just one line, very, very simple. Okay. Okay. Once you do this, you get this. Now you see this particular thing and this particular thing, this is less than delta, right? That's given to you. So essentially, this whole thing can be made less than epsilon, where epsilon is equals to delta 1 minus t naught. So basically, delta, which you need to find delta, right? So given this epsilon, you can just choose delta to be epsilon by t minus t naught, and then you will have this result. Okay, right. Why this is true? Because you see, let's say this particular thing. So this is, let me give you an idea. This particular term, the first term is basically delta by 2. This term is again delta by 2. And this term is less than, you see, delta again. Yes. So this is plus delta, and then integral by 2c, yeah? 2c integral x naught minus ct to x plus ct, x minus ct to x plus ct, and then 1 d tau, right? Because delta I took it outside, right? So this is always dominated by this. This particular term is always dominated by this. And then these two will give you delta. And then this term plus delta by 2c. This will actually give you x plus ct minus x plus ct. So essentially this is getting cancelled out. It becomes 2 times ct. This is getting cancelled. You see, this is delta plus 2t delta. Here, this t has this upper bound t naught. So essentially you can write it as delta. So this is always dominated by plus 2 t naught delta, which is 1 plus 2 t naught times delta. Is it okay? So we can just write down this delta like this. Delta equals to 1. Oh, sorry, I wrote it like 1 plus t naught. Delta. So this is your epsilon. This is your epsilon. So delta is epsilon by 1 plus 2 t naught. We can choose it like this. Yeah. Let me write it like this, where delta is epsilon by 1 plus 2 t naught. Yes. I hope this calculation is fine. So what is the idea? The idea is this: if you are giving me an epsilon, so you are basically telling me that I want our solution to be arbitrarily close to this particular thing. So whatever this is, and how do I get it? We get it using the fact that for this time between 0 and t naught, you will have a delta such that this particular thing works, right? Okay, so we'll look at some more problems and then we'll see what can we deduce. Okay, so let's look at an example of again. Yeah, see, let's say you are given this problem: utt equals to c square uxx, and then x is in R, t positive. Clear? And u at the point x here is sine x and ut at the point x0 is cosine x. Cosine x. Clear? So we need to know that if we can how to solve this problem. So essentially we want to find out what is u of xt. So therefore what is u of xt? It is nothing but half sine of x plus ct plus sine of x minus ct, and then I have 1 by 2c, right? X minus ct to x plus ct, and then what is it? Cosine tau d tau. Yes. So you just put it in the formula, right? You see, now if you just calculate it from this particular thing, you can get this is sine x cosine ct and then plus 1 by c. Calculating this thing, what do you get? It is cosine x sine of ct. See, this is very simple. So you don't have to do anything. Yes. And by the way, this formula you can of course use it without any restrictions. Okay. So you see, this problem may look very difficult, but if you use D'Alembert's formula, it is actually going to be trivial. Okay. So this is how you solve it. Okay. So what now we need to know is this. See, there is this thing. Let's just say that we look at this x and t. Let's just look at it. And let's say you have a point x naught t naught. That's the point x naught t naught. Okay. See, the thing is this. If you look at this formula, what is the formula? D'Alembert formula, that is. Yeah? Maybe here. Let me write it like star. Okay. So if you look at star, you see, if you take the point x naught t naught, right, as I have told you, it depends on the this thing, right, domain of dependence. Clear? So essentially the domain of dependence in this case is x naught minus ct naught and x naught plus ct naught, right? That's the domain of dependence. Clear? Okay. And the thing is this, there is something called the range of influence, right? So you see, so this is the domain of dependence. There is something called a range of influence. Range of influence. I will explain to you what that is then. Range of influence. So what is the range of influence? Let's just look at it. See, the thing is this. If you have this point, the characteristics of this problem, you remember? See, we talked about this characteristic. What are those? X plus ct and what is the characteristic? Yeah, x plus minus ct equals to constant, right? So you see, essentially those characteristics, if you start from x naught t naught, it will look like this: x minus ct equals to c1, one characteristic. Another characteristic will go like this: it is x plus ct equals to c2. Is it okay? And this region is R. Yes. What I'm trying to say is this, that the thing is, if the initial displacement, so if an initial displacement okay, is located in a small neighborhood of x naught t naught. So x naught t naught is some point, yes, and let's say if the initial velocity, right, so g, that is basically located in that small neighborhood, so it can only influence, only the area t greater than t naught, okay, which is bounded by the two characteristics x minus ct equals to constant and x plus ct equals to constant. So c1 and c2. Clear? Okay. So what does that mean? It means that the initial displacement is this displacement, right? So you see, you have displaced the string, yes, and the thing is, this displacement, this propagates. What is the speed of the propagation? Dx dt, that is equals to the constant c. Yeah, that is how you are getting the, so this is your characteristic equation, right? That is how you are getting the characteristic solutions. So this is a characteristic equation. So this is the speed with which this gets displayed, And the thing is this sector R. So you see in this part, what happens is uh, the displacement. So basically the effect you can just only see only in that part. So this infinite sector, okay, so this infinite sector, okay, R is called the range of influence, the range of influence. Okay, I hope this is clear. Yes. Okay, so this is the range of influence. So essentially, for given a problem like this, let's say this problem, so this is a question: find the range of influence, and the domain of dependence, at, let's say, for the problem, this problem, yes, this problem, let's just say A, of A at 1 1. Yeah, so basically x naught t naught is 1 1. Try to find what is the range of the influence and the domain of dependence. Is it okay? Right. So essentially what I'm trying to say is this: the solution only influence those points. So basically you see any other point here, this gets actually influenced only I mean with the whatever the solution does within this cone, right? That's the range of influence. Okay. So with this I'm going to end this video, and in the next video we are going to continue our study of wave equation. Thank you.